So as I told you, the pressure and temperature are the two important factors or two important parameters in supercritical fluid chromatography, because they are going to suppress or they are going to improve the extraction efficiency, especially in this separation technique. So there will be a pronounced effect while using the supercritical fluids, especially while playing with the pressure, just like what we do in gas chromatography and liquid chromatography. In gas chromatography, we will be programming with the temperature in order to do the gradient dilution. And in liquid chromatography, we will be keep on changing the mobile phase composition while doing the gradient dilution process. So temperature programming or mobile phase programming will be done in order to increase the separation resolution in GC and HPLC respectively. And all those things are dependent upon the capacity factor. Capacity factor and the retention time can be adjusted. That means to say that the chromatographic conditions can be optimized by adjusting the capacity factor and the retention time in such a way that there must be very minimum overlapping of the separated peaks in the chromatogram. So as a minimum overlapping is seen, the resolution will be maximum. So with this maximum resolution, we can say we have almost achieved the chromatographic separation. So capacity factor and the retention time are the two important parameters in order to attain the resolution of required level. How do we do this in supercritical fluid chromatography? This will be done. The attainment of the capacity factor or the retention time means to say that the retention time of the second solute or any one of two solutes must be increased in order to increase the resolution, and the capacity factor must be adjusted in such a way that neither rapid elution of the solute nor a longer time to get eluted must be expected. In such a way, we have to adjust the capacity factor and the retention time. So this will be done by programming with the pressure in supercritical fluid chromatography. Say for example, the elution of hexadecane is taken as an example, very interesting example this is. So this has to be eluted by means of supercritical fluid chromatographic column, which may be containing silica as a stationary phase and supercritical fluid carbon dioxide as a mobile phase. If you adjust the pressure at 70 atmosphere, the retention time for hexadecane will be 25 minutes. The retention time for the solute, the retention time of hexadecane at the pressure 70 atmosphere will be 25 minutes. So if you increase the pressure to 90 atmosphere, the retention time has been reduced almost 5 times. So 25 to 5 minutes. Initially it was 25 minutes, and that has been decreased to 5 minutes. That has been lowered to 5 minutes, lowered by a factor 5. So not only the analytical time is decreased, but also more number of samples can be subjected for separation. So the achievement of the separation will become reliable, will become selective for the separation of more number of solutes present in variety of the samples. So this is called as pressure programming. So this is same as we will be doing in GC by programming the temperature, and even we will be programming with the pressure. Not only the mobile phase composition will be varying during the gradient dilution process, but also the pressure programming will also be done. So the common pressure programming in SFC will be either constant by maintaining the constant pressure. We will be maintaining either constant pressure during the elution process, or we will be increasing the pressure either linearly, asymptomatically. So either linear increase or asymptotic increasing the pressure up to the final pressure will be done during the elution process in supercritical fluid chromatographic separation. So even the mobile phase gradients can also be used as organic modifiers in order to increase the selectivity of the separation. The mobile phase composition is also very important. So how do we do this pressure programming? This pressure programming is very important in order to adjust the capacity factor K dash and in order to decrease the retention time of the solute. Therefore, the column efficiency or the selectivity of the column can be enhanced to the required level. You can see here the chromatograms obtained for the separation of 6 compounds, 6 cholesterol derivatives. You can see at the bottom cholesterol actinoate, cholesterol decylate, cholesterol laurate, cholesterol myristate, cholesterol palmitate, and stearate, etc. All these 6 compounds are present in a sample as a mixture, you assume. And when they are subjected for separation by using Db1 and carbon dioxide as a mobile phase at 90 degrees Celsius by using flame ionization detector, if you maintain a pressure of 3000 psi under isobaric condition, almost 15 minutes, more than 15 minutes required to elute the 6th compound, that is cholesterol stearate. Cholesterol stearate. And not only the longer analytical time, but also the width, the baseline width of each and every chromatogram was very high under the isobaric elution. If you switch over the isobaric elution to the linear pressure gradient programming from 3000 to 4000 psi in 15 minutes, not only the analytical separation time has been reduced, but also the baseline width of each and every chromatographic peak has also been reduced. So this reduction of the baseline width will become consequence for reducing the band broadening, and hence the height of the theoretical plate will be decreased. Therefore, the column efficiency can be increased. So this slide reflects on the influence of the pressure programming and the success of the separation science. So what are the commonly employed stationary phases in supercritical fluid chromatographic technique? Although stationary phases, say silica or alumina, these two are the important stationary phases or important packing material which are very useful for the separation of non-polar compounds. Even polar compounds can also be separated. But while using them as stationary phases for the separation of polar compounds, some unwanted adsorption will be the consequence, and this must be eliminated by chemical treatment of the stationary phase. So all those stationary phases which can be used in GC and LC can also be used in supercritical fluid chromatographic technique. And apart from this raw silica and alumina, even bonded silica can also be used. And as I told you, by chemical treatment, by infusing the functional groups such as octyl group or octadecyl group or cyanoalkyl group or aminoalkyl group or dialalkyl group, the silica can be modified into modified silica. Therefore, the polarity can be regulated. As the polarity is suppressed, the physical adsorption can be suppressed, and hence the band broadening of the channeling can be reduced. And this bonded silica can also be mixed with organic modifiers in order to regulate the retention time, in order to adjust the retention time, and in order to adjust the capacity factor, and thereby the overall resolution can be enhanced. And widely used polar stationary phase, mainly polysiloxanes, because they are very stable and they have flexible silicon oxygen bond, and they will become responsible for the good diffusion of the solute through the surface of the stationary phase. So some polysiloxanes are also substituted with chemical groups in order to initiate the selective interaction with the analyte. And because of this selective interaction with the analyte, these stationary phases are going to function more selectively. And even polymethyl siloxanes or polydimethyl siloxanes can also be used for the increased efficient separation of polar components. And even cyanopropyl polysiloxanes are very useful for the separation of the compounds with carboxylic functional groups. And these are about the stationary phases. And the mobile phases, generally non-polar compounds with low to moderate critical properties such as carbon dioxide, nitrous oxide, ethane, and pentane are used as mobile phases in supercritical fluid chromatographic technique. And both the forms such as normal phase and reverse phase separations are also possible in supercritical fluid chromatography. Normal phase separation means the polar stationary phase and non-polar mobile phase, and reverse phase separation means non-polar stationary phase and polar mobile phase. The polarity of the mobile phase can be attained by mixing with the organic modifiers. So normal phase separations can be performed by using normal polar mobile phase such as carbon dioxide and dinitrogen oxide, and low polarity stationary phase such as amino or diol or cyano substituted silica. Low polar stationary phases such as amino, diol or cyano substituted silica, which are low polar stationary phases. So the elution is dependent upon the functionality of the molecule and also the polarity of the molecule and also the molecular mass. Here, we cannot predict whether hydrogen bonding is going to be taken place, whether van der Waals force of attraction is going to be taken place, whether electrostatic force of attraction is going to be taken place. whatever, we cannot predict. But the elution order is solely dependent upon the function of the molecular mass, polarity, and the functionality of the molecule which is present in the sample. As I explained yesterday, carbon dioxide is one of the mostly used supercritical fluids because it has very low critical temperature of around 31 degrees Celsius, and this is same as operating temperature, and up to 40 degrees Celsius we can operate while using supercritical carbon dioxide. And it has also got a moderate critical pressure with the density of around 0.5 gram per ml, and it will reach a very high density at the pressure less than 40 megapascals. So that's what the carbon dioxide is a excellent supercritical fluid. Moreover, it is very safe to use because it is non-toxic. It do not catch any fire, so it is non-flammable, and it is not going to exhibit the corrosive property. It is non-corrosive, and it is highly inert. It is highly inert. That's what we are living safe in the presence of carbon dioxide in the atmosphere. And this gas is also compatible to detectors what we will use in SFC technique, and it has a wide range of density. Therefore we can manipulate with the density regulation so that carbon dioxide can be converted into supercritical one. And as I told you, other supercritical fluids are nitrous oxides. It is very similar to carbon dioxide, and even some alkanes can be used. You have to be very careful while using alkanes because they will catch fire. Therefore, they are less safe. And one more problem is they are not as selective as carbon dioxide when compared to detector compatibility. And the advantage of using alkanes as mobile phase is they have better solvent characteristics for non-polar solutes, because as the number of carbons present in the alkyl group is increased, the polarity is going to be decreased. So they are non-polar. Therefore, they will become more selective solvent for the separation of non-polar components. And even some hydrocarbons, including xenon, can also be used as a mobile phase. But only special compounds can be subjected for separation. While using halocarbons, you must be very careful. The electron releasing will be taken place. And halocarbons, particularly in the hydrocarbons, you cannot use because they are flammable. And more polar solvents for the separation of highly polar components, and the molecular weights of the components whenever very high, these type of mobile phases can be employed. And not only the single solvent can be used as a mobile phase, and as we saw in the supercritical fluid extraction, some organic modifiers can also be mixed with the mobile phases. And the carbon dioxide, nitrous oxide, alkanes, halocarbons, xenon, all these things can be mixed with organic modifiers. Why do we mix the organic modifiers, or why do we use these mixed fluids as mobile phase? Because they will enhance the solubility of polar analytes in the supercritical fluid. Say, for example, if you mix carbon dioxide with methanol, the polarity of the supercritical fluid will be increased. Therefore, the solubility of the polar analyte in this mobile phase will be increased. Therefore, the retention of the solute in the mobile phase will become increased. And they will reduce the retention time. As a result of the reducing retention time, the separation time is going to be reduced to the maximum extent. And they also eliminate the strong interaction between the adsorptive site of the stationary phase and the polar solute. If we use more selective mobile phase, more the selectivity of the mobile phase towards the analyte, there will be less chances of interaction of that particular solute with the stationary phase might take. Therefore, the channeling will become lower, and hence the column efficiency will become higher. And these organic modifiers will modify the polarity of the eluent, that is the solvent what we are going to use, and that is again dependent upon the dielectric constant of the solvent what we will use, and also the polarity index. If the polarity index is very high, the polarity of the mobile phase will be consequently very high. Therefore, the separation efficiency can be maximum. As a result of using the organic modifiers, the retention factor, the capacity factor, along with the selectivity factor can be affected to a required level. Therefore, the identity of the modifier is a fingerprint in order to regulate the polarity of the mobile phase. Thereby, we can achieve the separation by using the mixed fluid state as a mobile phase. So, rather than using a single fluid as a mobile phase, in the presence of the organic modifier, the mobile phase is going to exhibit the increased functioning during the separation process in supercritical fluid chromatography. And what are the commonly employed solvent modifiers we will use in supercritical fluid chromatography? Mainly methanol. Low molecular mass alcohols can be used, including methanol, isopropanol, and other organic compounds such as dichloromethane or methylene dichloride, tetrahydrofuran, acetonitrile. So when you mix these type of compounds with supercritical carbon dioxide or ammonia or N-butane or alkane or halocarbons or xenon, the organic modifiers will increase the solvent strength. Therefore, in the heliotropic series, the elution capacity of the mobile phase with respect to analyte will be enhanced. Therefore, the solvent strength will become greater when you mix the fluid with the organic modifiers such as methanol, isopropanol, dichloromethane, tetrahydrofuran, and acetonitrile. You can see here the tabulated form of plenty of supercritical fluids and a critical temperature, critical pressure, and the density at the critical temperature and pressure. So as I told you, carbon dioxide, it is having very low critical pressure, and it has also got an advantage of low toxicity and non-inflammability, you can see here. And nitrous oxide is also comparable with carbon dioxide. Isopropyl diethyl ether can be used for the separation of polynuclear aromatics and polymers, and along with them dimethyl ether, methyl ethyl ether, and diethyl ether. But they are having critical temperatures of 125, 165, and 193. Very high critical temperature needs to be maintained. While maintaining such a high temperature, we must be very careful because these are ethers. They easily catch the fire. We must be very conscious while using them. But the critical pressure 52.6, 43.4, and 36.3, there is no any difficulties arise while adjusting the pressure to above the vapor pressure. And if you look at the density, their density is very low when compared to carbon dioxide and nitrous oxide. Therefore, their disadvantages, of course, even with these disadvantages, we can employ them for the separation of polynuclear aromatics as well as polymers. And even some hydrocarbons can also be used, including ethane, ethylene, propane, N-butane, N-pentane, and benzene, which are also having the critical temperatures of 30 to 10. You can look at ethylene is having very low critical temperature. So 96.8 degrees Celsius for propane, 289 for benzene. And similarly, the critical pressure of 48, 51, 42, 37, 41, 48, etc. And if you look at the density, N-pentane is having very high density, 0.554, and this will become more selective fluid, especially for the separation of compounds which do not catch the fire. So you must be very careful while adjusting the temperature to 196.6 degrees Celsius. Mostly oligomers are separated by using this N-pentane. Special design must be made while using this N-pentane as a supercritical fluid. And apart from all these supercritical fluids, even fluorocarbons such as trifluoromethane and tetrafluoromethane can also be used. 25.9 degrees Celsius will be the critical temperature of trifluoromethane, whereas tetrafluoromethane will be having minus 45.7 degrees Celsius. So some special arrangement needed to be made while using tetrafluoromethane as a supercritical fluid because regulating the temperature to minus 45.7 degrees Celsius is somewhat difficult. So we may have to use special devices. Cryogenic cooling needed to be made while adjusting the temperature. But the density is advantageous here, 0.628. Very high density is exhibited by this species. Therefore, this is going to be the suitable fluid for its use as a mobile phase. And these are some modifiers what we will use. Methanol, ethanol, propanol, 2-propanol, 1-hexanol, 2-methoxyethanol, tetrahydrofuran, 1,4-dioxane, etc. So they also got their own critical temperature and pressure, or their molecular masses are also given. Molecular mass must be always very low. If the molecular mass is very high, their viscosity and the diffusion coefficient will also matter, and the effusion of the solute will be suppressed if the molecular mass is very high. And you have to look at the polarity index. If the non-polar is the fluid and the polarity index for methanol is 5.1, it is polar. And when you mix the carbon dioxide with the methanol, the polarity of the mixed fluid of carbon dioxide and methanol will be in between 2 and 4. Therefore, it is suitable for the separation of polar solutes. Similarly, ethanol, acetonitrile, you can say. So water is also present in the series, which is having polarity index of 10.2. 10.2. It is a highly polar solvent. Water is a highly polar solvent. That's what it is a suitable. It is called as universal solvent for the dissolution of variety of the compounds. So the ultimate requirement in order to perform the separation by SFC is the mobile phase composition, and that can be attained by mixing the fluid with the modifiers such as low molecular mass alcohols, carboxylic acids, dimethyl formamide, 1,4-dioxyacetonitrile, etc. So you must be very cautious while mixing these modifiers with the fluids. In order to get the mixed fluids, they must be miscible. They must be miscible. Before converting the fluid into supercritical fluid, they will be in the liquid state. And when you mix the liquid with the liquid of the organic modifier, they must be miscible. They must be dissolved to each other. Then only we can use them. The pair of the supercritical fluid and the organic modifier must be miscible over the range of the temperature and pressure what we are going to use during the separation process. If they are immiscible, no use. So you must consider this parameter also. Then let us move on to the detector. What are the detectors we will use in supercritical fluid chromatography? So liquid chromatographic detectors are also employed in supercritical fluid chromatographic separation. Not only LC detectors but also GC detectors can also be used. But you must be very careful. Closed cell must be used while using all those LC detectors, because the solutes must be reaching the detector in the presence of a supercritical fluid. So fluid must be maintained under the pressure, but it must be cool to the liquid. It must be cool to the liquid. Therefore, the closed cell must be used. While using GC detectors in open cell, fluid is going to be decompressed to gas, because the mobile phase will be in the vaporized state and the solutes are also converted into vapor state. Therefore, the fluid must be decompressed to gaseous state. And under ambient pressure, the ionization detectors can be used. Say, for example, flame ionization detector can be used for the separation of organics. I have already explained the principle of flame ionization detectors in gas chromatography. And hydrogen atmosphere flame ionization detector will be used for the separation of organometallic compounds. Thermionic detector will be used for the separation of nitrogen phosphorus containing compounds. Electron capture detector will be used for halogenated compounds, because they will be containing more electronegative groups. As a result of the presence of the more electronegative group in these halogenated compounds, the electron availability will become very simpler, and these electrons are going to be captured by the detector very easily. And even photoionization detector can also be used for the separation of organics, which are having 10.2 electron volts of ionization potential. All these things are basics, the ionization potential and everything with respect to organics. And even ion mobility detector, which will respond with respect to the mobility of the ions, and in such a way the detector is going to be devised. And therefore this detector is going to detect high electron or proton affinity compounds, so which are having the ability to release a more number of electrons, or protons availability in the compounds can be easily detected by these ionic mobility detectors. And even some optical detectors can also be used, such as UV absorption detectors, Fourier transform infrared detectors, fluorescence detectors can also be used. A flame photometric detector can also be used for the compounds containing sulfur, phosphorus, and chemiluminescence detector can be used for the compounds containing sulfur, and those compounds which have the ability to undergo easy oxidation. And even element selective plasma emission detector can also be used, which is more selective for the detection of elements of the compounds present, especially nitrogen, sulfur, phosphorus, etc. Light scattering detector can also be used whenever the solute will become responsible for the scattering or the reflectance or refractance. So therefore, light scattering detector is also used. And in the vacuum atmosphere, mass spectroscopic detectors will be used with many modifications, such as electron spray ionization detector with ionization chamber, and ionization chamber will become responsible for the fragmentation of the molecules, and the molecular masses of the fragments will be measured by means of these mass spectrometric detectors. So these are the variety of the detectors so we will be using in supercritical fluid chromatographic technique. If you look at here, the principle of each and every detector you must understand. Flame ionization detector means there will be a collector electrode and a repeller electrode. Due to the ionization process over the surface of the flame, the ions are going to be captured. Positively charged species are going to be captured by the cathode, and hence there will be a deflection. There will be increase in the current, and that current is directly proportional to either concentration of the solute or the relative positioning of the peak will be with respect to the solute present when it is compared with the standard. Similarly, thermionic detector, it is going to function based on the principle of thermal energy. An electron capture detector is going to function based on the principle of capturing of the electron. As a result of the electron capture, there will be a deflection in the current in the presence of the solute. And this deflection will be measured in between the mobile phase and the mobile phase in the presence of the solute. You know the principle of UV absorption detectors. The detector will be set at a wavelength of 250 or 254 nanometer or 260 nanometer or 330 nanometer or 365 nanometer, whatever it is. At that particular wavelength, the relative absorption or the transmission is going to be measured. And the stretching frequency is going to be measured while using IR spectrometer, while using fluorescence detectors. The emission intensity of a compound, if it is fluorescent nature, is going to be measured. Otherwise, the transmission is also going to be measured after the molecule is made to excite into the high energy level. So like this, the principle of each and every detector you must understand. And you can complete the supercritical fluid chromatographic technique with the capillary gas chromatographic technique and HPLC technique with respect to alpha means the selectivity and the capacity factor. So you can see by means of this particular plot that when we expect the resolution of 1.5 and capacity factor of 2, how many number of theoretical plates we are going to obtain in supercritical fluid chromatography. As you can see here, the technique supercritical fluid chromatography is placed in between gas chromatography and high performance liquid chromatography because you can attain the resolution of 1.5 with a capacity factor of 2 by obtaining the number of theoretical plates from 50 to around 80,000. 50 to 80,000 number of theoretical plates can be anticipated with the resolution of 1.5 and the capacity factor of 2 while using supercritical fluid chromatography. When you compare the performance characteristics of SFC, this is placed in between GC and HPLC based on the number of theoretical plates. So with this plot, we can come to the conclusion that HPLC is less sensitive when compared to SFC, where SFC is less sensitive when compared to GC while using capillary columns. So as a whole, gas chromatographic separation will yield more sensitive results when compared to SFC, but SFC will be having advantage with respect to mobile phase, with respect to regulation in the mobile phase composition. Therefore, the polar or non-polar solutes can also be separated in equal to the separation selectivity in GC. So these are the advantages of SFC. SFC is placed in between GC and HPLC because with the resolution of 1.5 and the capacity factor of 2, 50,000 to 80,000 theoretical plates can be anticipated. So this tabular column, couple of tabular columns will be tabulating the performance characteristics of supercritical fluid columns, packed columns and open tubular columns with low density and high density parameters. The velocity of the mobile phase is given here. So at 0.5 to 1.5 centimeter per second, the value of U, the average linear velocity of the mobile phase from 0.5 to 1.5 centimeter per second. The number of theoretical plates anticipated may be ranged from 3.3 K to 3.7 K, 3,300 to 3,700 plates can be expected. So the number of samples can be subjected 31 to 79 or 42 to 83. So efficiency or time range can be denoted as 31 to 79 or 42 to 83. Elution time you can see here 0.7 to 2 minutes. 0.7 to 2 minutes. the analytical time will be extended up to 30 minutes. So within 30 minutes, all 79 solutes can be eluted. So highly selective when compared to LC, and GC is highly sensitive as I told, but SFC is placed in between. So when compared to LC, SFC is advantageous with respect to number of solutes eluted and the number of theoretical plates. So as you can see by means of this table. And you recall the Van Diemter plot once again. This is also a Van Diemter plot which is showed here how the supercritical fluid chromatographic technique is more advantageous when compared to HPLC with respect to reduced plate height. With respect to reduced plate height. You can see here the Van Diemter's plot, how the height of the theoretical plate is going to increase with increased linear velocity of the mobile phase. As the average linear velocity of the mobile phase is increased, the height of the theoretical plate is also going to increase abruptly in HPLC. Whereas in case of SFC, as the average linear velocity of the mobile phase is increased, there is less rapid increase in the height of the theoretical plate, as you can see by this curvature, the wide curvature you can see in this Van Diemter's plot for SFC. Assume the linear velocity of the mobile phase is 0.6 centimeter per second for HPLC. If the linear velocity of the mobile phase is 0.6 centimeter per second, the height of the theoretical plate will be around 0.039 or 0.038 millimeter, the height of the theoretical plate. At the same velocity of the mobile phase, the height of the theoretical plate is going to be around 0.011 in SFC. So at 0.6 centimeter per second linear velocity of the mobile phase, the height of theoretical plate in HPLC will be around 0.038, whereas in case of SFC, this is going to be only 0.011. So this states that, this concludes that even if you increase the linear velocity of the mobile phase, this is not going to damage the efficiency of the separation. So in order to attain the height of the theoretical plate at 0.011, the linear velocity of the mobile phase in HPLC must be around 0.2. So if you adjust the linear velocity of the mobile phase at 0.2, the mobile phase will be moving very slow. Then the channeling of the solute will be consequent, therefore band broadening will be very high. So one advantage while using a separation technique of SFC is that even if you increase the linear velocity of the mobile phase by 4 times, we can decrease the height of the theoretical plate 3 times. Even by increasing the linear velocity of the mobile phase 4 times, the height of the theoretical plate can be reduced 3 times. So the degree of overlapping in SFC will be very low when compared to HPLC. Therefore, this SFC technique is always advantageous in order to perform the separation.